Hello, hello again. Welcome back. We have one more lecture on vectors. Today we're going to be talking about cross products. So we've seen dot products in our last video. That was a way to take two vectors, multiply them together, and get a scalar. Cross products will let us take two vectors and multiply them together and get back a vector. But the algebra isn't going to work the same way as algebra with regular numbers do. And computing a cross product is a little bit trickier than the process of computing a dot product. So let's get started. How do you compute a cross product? Well, okay, there it is. It doesn't look terribly user-friendly there. What is that big box-shaped thing in the middle? Well, that's a matrix, and I'm taking the determinant of it by putting those vertical lines around it. In other words, what we do, we want to hit the cross product of, say, V1, V2, and V3 with W1, W2, and W3. Then I make a matrix. I put I, J, and K. Those are the I, J, and K unit direction vectors, the I, J, and K that we're familiar with when we write out a vector. We put I, J, and K in the first row. Then we take the V vector, right, put it in the second row, and the W vector and put it on the last row. Notice that the order matters. If it's V cross W, you have to put V first and then W. Okay? If you get the order wrong, then it changes the sign of or changes the direction of the vector when we're done. We'll see how that works in just a second. Well, once we've made our matrix, it's a nice 3 by 3 matrix, we take the determinant of it, that's the cross product. Okay? So this desperately needs an example and probably a reminder of how determinants work too, because if you're like me, by the time you get to Calculus 2, it may have been a while since you've done high school algebra and thought about determinants of matrices. So here's a pair of vectors. 2, negative 1, 3, and 0, 7, negative 4. And we want to find the cross product of these two vectors. So we make our matrix, I, J, and K in the first row. The first vector has to go first, 2, negative 1, 3, and the second vector then goes after that, 0, 7, and negative 4. We have to find the determinant of the matrix that's left over. Okay, so it's a 3 by 3 determinant. If you are a little rusty on how that works, we're going to go through how to find determinants slowly and carefully so you see how this works. The first step is to cross out, to go along one row or column and cross out the row or column that intersects there. We're going to go across the top row as we do this, expanding along the IJK row, because it's much, much easier. And that will give us the answer with some number times I, some number times j, some number times k. So look at the I, and I'm going to cross out the row and column that intersect there at the I, right? So put my finger over that row and that column. And what's left is a 2 by 2 matrix. So the first step in finding the determinant of this 3 by 3 matrix is to cross out the row and column that intersect at I and look at the matrix that's left, find its determinant, and multiply it by I. Right? So I've broken this matrix up into this 3 by 3 matrix, and I've carved out a 2 by 2 matrix, negative 1, 3, 7, and negative 4. I've got to find the determinant of that smaller 2 by 2 matrix and then multiply it by the I. Next, I do the same sort of thing with the j. Right? I cross out the row and column that intersect at j and look at the 2 by 2 matrix that forms. So that'll be 2 and 3 and 0 and negative 4. I multiply that by j. But notice that the middle term here gets a minus sign. So what's happening is the signs are alternating as we go across. It's going to go plus the first time, minus the second time, plus again with the last time. So when I get to the k, I cross out the row and column that meet there with k, and that leaves me another 2 by 2 matrix, 2 and negative 1, then 0 and 7. That determinant gets multiplied by k. So the only part about this is a little tricky, is making sure that we put the minus sign right there on the middle determinant, the one that goes with j. Okay, so now I have to do 2 by 2 determinants, right? I'm going to explain this the way that I learned it because I think it's kind of cool and because everybody usually laughs when I tell this story. So I hope you do too. When I learned this in my math book, in the 1980s, um, in Mississippi, the book had a picture of the United States, something like this. And in the picture, they had drawn in a couple of arrows. So there was an arrow that went this way, like toward Florida, and an arrow that went that way toward like New England. And then down near Florida, there was a bright, happy sunshine picture. And up near New England, there was rainy, cloudy, snow, blizzardy looking, awful, cold looking picture. Okay? And the idea was this was supposed to help you remember the way that the signs work when you multiply in certain directions to calculate this 2 by 2 matrix. So hopefully this will help. If not, then remember it however you want to. But the way that the picture is supposed to remind you to do this is you multiply in the Florida direction. So the -1 times the -4 in that very first matrix. Then you multiply in the New England direction, the 7 times 3. Okay? So you take those numbers, and now the reason that the sun and the snow are there is because multiplying in the Florida direction gets a plus. Multiplying in the New England direction gets a minus, right? And again, growing up in Mississippi, that made perfectly good sense that bright sunshine should live in the direction that the country that I live, and up north where it seemed to be cold all the time, that seemed like the negative and snowy direction. So with numbers, this would turn out to be -1 times -4. Okay? That has a plus in front of it, right? Then 7 times 3, but he gets a minus sign with that. Okay? So, okay, let's erase all the pictures and go back to just doing numbers. So I would have -1 times -4 minus 7 times 3. And that gets multiplied by I. Then I do the determinant for the j. So that will be 2 times -4 minus 3 times 0. Okay? And again, there's an extra minus sign in there because it's the middle term in the doing the 3 by 3 determinant. Then I have 2 times 7 minus 0 times -1. Okay? That gets multiplied by k. And you do the arithmetic and out pops something like -17i plus 8j, then plus 14k. So that's a little bit more involved than finding a dot product, right? You have to do a 3 by 3 determinant, which means doing 3 2 by 2 determinants. The only part about it that's really hard, though, is just not making a silly mistake with a minus sign or doing something weird when you do the multiplication, right? So the numbers, of course, on the test will be small enough that you can do the multiplication and any of the addition that you have to do, with pencil and paper. You want it to be anything that you need a calculator for. But you do have to be a little careful not to let yourself get thrown off by multiplying something wrong or messing up a minus sign. Okay, well, there are some weird things about this cross product that don't normally happen with normal multiplication of numbers. For example, if you take v cross v, you always get 0. That's a weird kind of multiplication. That's what I meant earlier when I said there's not a way to take two vectors, multiply them together, two vectors in 3 dimensions, multiply them together, get a vector back, and have the multiplication do the kind of algebra that we're used to. I mean, so this is a way to multiply 2 vectors and get a vector, but the algebra, it looks weird when you write it down like this, right? V cross V, right? I mean, wow, you get 0. Okay? Also really weird, V cross W is minus W cross V. And of course, the reason for that is you have to put the vectors into that matrix, right, in the order in which they appear. So if you have V cross W, the V goes into the matrix before the W. If you switch it around and do the W first, that changes the sign of the determinant. Also, you have this weird looking fact, right? If you take V cross W and then dot it with V or dot it with W, you get 0 every time. Whoa, wait a minute, what does that mean, right? Well, remember, what happens if you take a vector and dot it with another vector and get 0? It means the two vectors are perpendicular. So this says that v cross w is perpendicular to both v and w. And so there'll be some homework questions that say, find a unit vector perpendicular to these two vectors that they give you, v and w. And if you take v cross w, that'll be perpendicular to both, and you can divide by or multiply by 1 over the norm, and then make it into a unit vector. So if I were able to video myself doing this, which I guess I could, but nobody really wants to look at me, I could hold up my hand and show you how to do this right hand rule. So what you do is take your index finger, your pointer finger, and point it in the direction of V. Okay? Then take your middle finger. You have to be really, really careful when you explain this to a class full of smiling and somewhat naughty 18-year-olds. Take the middle finger, point it in the direction of W. Right? If you do that, then your thumb of your right hand will automatically point in the direction of V cross W. Right? If you tried it with your left hand, you'd get the direction of W cross V. So you always want to do this with your right hand. Do the first thing, right? And if it's V cross W, you do the first vector with your pointer finger, the second vector with your index finger, and your thumb will point perpendicular to both of those, right, in the direction of the cross product. We do at least still have something that looks like, a distributive property. That still works. And also this other thing that kind of looks like what happened with a dot product. Remember, v dot w was norm of v, norm of w, cosine of the angle between the two vectors. Well, if you take v cross w, then take the norm, that's a little different. You have to take the norm. Then that equals the norm of v times the norm of w times the sine of the angle between them. Now, normally, if you just want to find the angle between two vectors, we wouldn't do it this way, right? But you could. You could calculate the cross product and use that instead of the dot product. It'd just take a little longer. What this is really useful for, though, is it lets us get at some other cool geometry. For example, suppose I had two vectors, v and w, draw them like arrows, and I use those to make a parallelogram. So you see how I do that, right? That's the v and the w are making, one corner, right? But then it's really easy just to sort of finish that out and make the rest of the parallelogram. Well, it turns out that if you take v cross w and take the norm of that, that equals the area of the parallelogram. And of course, the reason is the area of a parallelogram is what? The base times the height. So in this picture, the base would be the length of v. The height would be, well, the length of w times sine of theta, right, would give us the height. If you just made a triangle out of v and w, that'd be half of a parallelogram. So the area of that triangle would be half of the norm of v cross w. This is a useful fact to file away, because what typically happens on final exams and such is a question gets asked, find something that you have to use the dot product for. So sometimes it's the angle between the two vectors. Sometimes it's, are these two vectors parallel? Or are these two vectors perpendicular? Sorry. Something you have to do with the dot product. Then there's usually a question to find something that you use the cross product for. It might be find a vector perpendicular to the two that I gave you. Or it might be just find the cross product. Or it might be find the area of a parallelogram spanned by these two vectors, which means you have to find the cross product and then find the norm. So another cool geometric property of the cross products is it lets us find volumes. So suppose we have three vectors, u, v, and w. They are all pointing out, from the same point. And we use those to make a box the same way that we use just two vectors to make a parallelogram a second ago. So we call that kind of a box a parallelepiped. That's the fancy geometry name for that. If you want to find the volume of that kind of box, all you have to do is take two of the vectors, find the cross product, then take that and dot it with the third vector. Sometimes that's called a scalar triple product. Then take the absolute value of the number you get out of that. That gives you the volume of that box, of that parallel pipette. Finally, one more thing you can do with a cross product. Suppose that you have a point which is rotating around another point. So imagine that you have a point on a wheel as it's spinning around. Right? So the point O for origin is sitting at the center of a circle. The point P is rotating around it, right, on the circle. And there's a force that's acting on P tangentially. So imagine that this is like a belt attached to this wheel that's making it spin. The force is acting tangentially, like a pulley on this wheel, or a belt attached to it to make it spin. Then the torque is given by taking the cross product of the vector from the center to the point on the wheel, the vector OP, crossing it with the force, and then taking the norm of what's left of that cross product. So that's cool, right? Cross products give us torque. Dot products gave us work. So you can see, of course, why this shows up in physics so often. So anyway, again, if you have any questions about the vector stuff, for most people, they've seen this sort of thing before in physics, and it's not that weird and scary. But if this is weird or scary for you, if you haven't seen this before, be sure to send me an email. We can visit about this and make sure that we get all this figured out so that it's easy for you as well.